Okay, in the case studies initially we discussed about arithmetic logic unit and then register file. So, which will act as a small memory which is present inside the CPU. Okay. And the other case study that we are going to discuss today is static random access memory. So, as we have discussed in the earlier lectures also. So, if we take the CPU or the microprocessor. So, difference between the microprocessor and CPU is a CPU built into a single integrated circuit is called microprocessor. So, here we have arithmetic logic unit which is one of the important block, and then we have the register array or register file. This is the register file which we have discussed in the previous slides. Okay. Now, the memory is external to this CPU. So, this register file will act as a small memory, but the main memory will be interfaced outside the microprocessor or CPU. Okay. Now, we will discuss about this memory. Again, memory, there are two types of the memories. One is called as static RAM and dynamic RAM. In random access memory, in read only memory also there are different types are there, but here we will discuss about the random access memory. So, in this static random access memory, is having some advantages, like it does not require any refreshing circuitry, whereas dynamic RAM requires refreshing circuitry. So, here I will discuss about the static random access memory. So, you take any memory. So, what are the different signals for the memory? We have discussed this in earlier lectures also. So, in the memory there will be some address lines which is unidirectional. Address lines, and there will be some data lines which are bidirectional, and then any chip will be having chip select. Normally in ICs chip select signal will be active low, but here for the sake of simplicity I am assuming active high signal. So, CS is equal to 1 means this IC is selected. Then we can read as well as write. So, there is a read signal, then we have one write enable signal, and of course, we require the clock. So, this is the write enabled signal, read signal, chip select signal, clock. Then this data, as I have told, bidirectional. This data in is this direction, data is inputted, data out is this direction. This will be inside this will be outside this. Similarly, address, there will be some address line, this is unidirectional. Now, this address lines is going to decide the size of the memory. The address lines is going to decide the size of the memory. Okay. So, here I am taking 8 address lines. So, in general, if n address lines are there, the memory size is given by 2 raised to the power of n. So, this is equal to 2 raised to the power of 8, because n is equal to 8 in this case. This is I think 256 bytes. So, that means this memory will be having 256 different locations, 0, 1, 2, so on up to the last one is 255. 256 different locations. and this data line is going to decide the number of bits in each location, because this is also 8 bit. So, each location is capable of storing 8 bits of information. This will have 8 bits, this will have 8 bits. So, like that each location will have 8 bits of the information. Okay. Now, we can perform either read operation or write operation using two different read and write signals. So, in order to perform either read or write operation, the initial condition is chip select should be 1. If chip select is not 1, we cannot perform neither read operation nor write operation. Okay. So, we have written the Verilog code for this one and test bench and the corresponding waveforms. So, we can see here the module name is synchronous static RAM. So, we will call it as synchronous RAM. So, the inputs are data in is the input, data out is the output, address is input, chip select is input, write enable, read, clock. Then we are defining this later. So, on the parameters we are going to define as address as 8, data as 8 and data path is also 8. Okay. So, the number of bits to be processed. And then we are defining the input port as data in, this data in I am defining here. So, this is data minus 1 0, what is DAT is 8. So, this will be 7:0. So, this is total 8 lines, this becomes 7:0 because DAT is 8. Okay. Similarly, output register. So, this also again 7:0. So, 8 bit data in, 8 bit data out. Then address is also 8 bit because ADR is 8, this is also 7:0. And these are single bit signals CF, CS, chip select, write enable, read, clock. Okay. Then the internal variable, okay, this is external register, we have defined this as register, external register we have defined as data out. Okay. So, this data out will be taking the data from the memory. So, we can call this inside this memory. So, we can have 256 locations. So, we are calling this SRAM data minus 1 7:0, yes, SRAM 7:0. So, whatever this data that is available here as 8 bits, this we are calling as SRAM 7:0. So, this data we are going to output onto this data. Okay. So, that is why this is internal variable. Up to here it is initialization. Coming for the main program, always at positive edge of the clock, we are assuming that the clock is positive edge. Begin if chip select equal to 1, if chip select is 0, no operation. Okay. So, this chip will not be selected, we cannot perform neither read operation nor write operation. So, in order to perform either read or write operation, the primary condition is chip select should be 1. Then we are checking for the write enable and read. So, this is write enable is 1, read is 0, because these are active high signals, this will indicate write operation. So, in write operation what we will do? We will write some data into the memory. Okay, we will take the data onto the data in and we will write into the memory. So, what is SRAM? This SRAM is equal to data in, whatever the data that is taken in the data in will be write into the SRAM address that we have defined here. And on the other hand, if read is equal to 1 and write enable is 0, this is read operation. In read operation reverse, whatever the data that is available here, that will be outputted onto the data out. Okay. So, for that the assignment is data out is equal to SRAM address, these two are opposite. Then end, so this is the end module. So, this is actually behavioral modeling. So, we are not discussing about the internal circuitry of this synchronous static RAM. Okay. So, we just discussed about the external devices only, external the signals of the SRAM. Okay. Now, what is the corresponding test bench? This is the corresponding test bench. So, we have time scale. Okay. So, 1 nanosecond by precision of 1 picoseconds. Then we know that all the inputs will be declared as registers in test bench and all the outputs will be declared as wire. Then after initialization, then the next step is instantiate the design under test. Here I am using the same names, we can use the different names also, as you have discussed in the previous lecture with an example. So, here I have used the same names, dot followed by CS and then CS. Okay. So, this will give the connections between the test bench and the design under test. Okay. Now, initially data in, we are taking 8 hexadecimal zeros, means 0 0 0 0 0 0 0 0 H, and then address is also 8 hexadecimal. Chip select is single bit, 1 bit binary 0. Initially I have taken as chip select as 0. So, write is also 0, read is also 0, clock is 0. So, we will wait 100 nanoseconds for the reset, because chip select is 0 means it is some sort of a reset type of the operation. Okay. Then after 100 nanoseconds, I will take the data in as 0 0 0 0 only, address is also 0 0 0 0, the same thing I have taken, but this time chip select is 1, then write is 1, read is 0 means this is write operation. After 100 nanoseconds, it will perform the write operation, okay, with data as all zeros, address is also 0 0, means what does it mean? So, we are going to write in the first location, this is all zeros, 0 0 0 0. So, here we are going to enter all zeros for this assignment. Then after 20 nanoseconds, so I will make this data in is also 0, address is also 0. Okay. So, I will keep as it is, and then after 20 nanoseconds I will make all ones, means totally 140 nanoseconds. So, this data becomes all ones, address becomes all ones, the last one, these are all ones, this address is also all ones. Then after another 20 nanoseconds, I will make 8 bit hexadecimal 1 all zeros, 8 bit hexadecimal all 2s. After 20 nanoseconds, I am giving different values of data in address, different value of data in address. Okay. After total of this much time, the total time is 40 plus 20 plus 20 plus 20 plus the previous 120 it seems. So, now I will make this as a read operation, because write is 0, read is 1. Again for every 20 nanoseconds I will change the bit pattern of the address. Okay. Then for the clock I will use the similar type of the logic that we have discussed in the earlier examples. So, for every 10 nanoseconds clock becomes clock bar, means the clock period is equal to 20 nanoseconds, clock frequency is 1 by 20 nanoseconds. Okay. So, you can see the corresponding waveforms. You can see that initially for 100 nanoseconds the write signal is 0, read chip select is 0, write is 0, read is 0, that is what you have written in the test bench. Then after 100 nanoseconds we make chip select equal to 1 and then write operation, as I have discussed. This is write operation, because write equal to 1, read is 0. Okay. So, while writing also we will write, so whatever the data that is in and then address. Okay. So, in that address this data will be written. Okay. So, this is data out, this data whatever the data in is 1 is outputted here, 16 is outputted here, 6 is outputted here, okay, because the corresponding timings are 220 nanoseconds and the clock is complemented for every 10 nanoseconds. Okay. So, we can check these values from the values that I have given in the test bench, these values you can verify. Okay. So, this is about the next third case study, so which is on the memory. Okay. So, with these 3 case studies you should be able to design now any microprocessor. Okay. So, because the main blocks we have already discussed. So, arithmetic logic unit, register file, external memory, the remaining blocks are minor only. So, we have some control circuits like decoders, multiplexers. Okay. So, with this knowledge you should be able to design a CPU or microprocessor which can perform the different operations. You can vary the specifications, okay, the number of operations that is to be performed, the number of registers, the address width of the microprocessor, the data lines. Okay. By changing the different parameters you can design the different microprocessors. Okay. So, the next case study is on the digital filter design. This is also another important realization. Okay. So, the people who works on the Verilog implementation of DSP algorithms. Okay. So, one of the important DSP block is digital filter. Okay. So, how to implement digital filter using Verilog. So, we know that a filter is a frequency selective network. It selects some frequencies and rejects the remaining frequencies, okay, based on whether this is going to select the low frequencies, high frequencies, a band of frequencies, or it rejects the band of frequencies. We have basically 4 types of the filters: low pass, high pass, band reject. Okay. Again the filters will be broadly classified into 2 types. One is called as FIR, another is called IIR. FIR is finite impulse response. Or infinite impulse response. So, here we will not discuss about how to design this. So, designing of this filters will be studied at DSP course. Okay. Here in this particular course we will discuss how to implement these filters using Verilog. Okay. So, we will discuss about the Verilog code, then test benches and then the output waveforms. So, I will start with the FIR filter, later I will discuss about the IIR filter. So, if you consider a 3-tap FIR filter, the difference equation for the 3-tap FIR filter is, so y of n is equal to a into x of n plus b into x of n minus 1 plus c into x of n minus 2. So, this is output, this is input, these are the taps or weights. You can also call this as taps or weights. So, by properly choosing these A, B, C values, we can set the specifications of the filters that we are not going to discuss. Okay. Suppose if I take a low pass filter, so ideally it should be passes all the frequencies from 0 to WC with unity gain. It has to reject all the frequencies beyond WC. Okay. But practically you will get something like this one. So, there are 4 parameters basically. One is called as pass band gain, pass band frequency, stop band gain, stop band frequency. So, this parameter to satisfy these parameters, we will design a filter. So, accordingly we will fix ABC. So, that filter design you might have studied DSP course. Now, here we will discuss only implementation. Okay. So, here basically we require 3 multipliers, which says some Tm is the computation time of each multiplier, and 2 adders. So, initially I will start with a simple multipliers, which is unsigned multiplier. Multiplier can be either signed or unsigned. But in most of the practical applications we need the signed multipliers only, because the data can be either positive or negative. Okay. But in order to better understand this filter, I will first start with the unsigned multiplier, then later the IIR filter I will implement with the signed multiplier. Okay. FIR filter I will use unsigned multiplier. Okay. One of the important unsigned multiplier is Braun multiplier. And then this adder you can use any of the adders, but I will use here ripple carry adder, which we have discussed in the earlier lectures. This adder we are going to multiply with ripple carry adder, this multipliers with Braun multiplier. Then I will implement the FIR filter. So, for that initially we have to implement Braun multiplier. You write down the Verilog code, then Verilog code for the RCA, then Verilog code for this delays, which are D flip flops. This I already have discussed in the earlier lectures, this also I have already discussed. Okay. So, now we will discuss about the Braun multiplier here, and then we will instantiate this D flip flop, Braun multiplier and RCA to implement the final FIR filter. Okay. So, to start with this, we will first discuss about the Braun multiplier. Braun multiplier is unsigned multiplier, as I have told. Okay. If I consider a 4 bit by 4 bit multiplier, this requires in general for n, sorry, this is n actually, n bit by n bit multiplier, we require n into n minus 1 full adders. If I take n is equal to 8, this will be 8 into 8 minus 1, which is 56 full adders are required. And to generate the partial products, we require the AND gates. Okay. The number of AND gates required is simply n into n. N is 8, so total 64 AND gates are required. Then as usual in any multiplication, we will first find out the partial products and then we will shift and then add. Okay. So, this will be better understand from the algorithm in the next slide. So, I have taken basically 2 8-bit numbers A7, A6 so on up to A0, B7, B6 so on up to B0, where A7 is MSB, most significant bit, and A0, B0 are LSBs, least significant bits. Then we will perform this multiplication in the conventional manner. We will multiply first with B0, A0, B0, A1. Okay, we will put the values here, then we will shift and then we will put the values. So, like that this is the complete table. So, here to get the final 16 bit output, we are performing 2 8-bit by 8-bit multiplications. The result can be, maximum result can be 16-bit. Okay. So, that 16-bit result will be shown by P15 to P0, this is LSB, this is MSB. Then how to implement this P0 to P15? So, P0 implementation is basically AND gate. Okay. Nothing is to be added, AND gate. So, totally we have to generate all this partial product. This is a partial product, this is another partial product, this is another partial products. Okay. So, totally we have 8 partial products. Once if we generate the 8 partial products, then you can perform the addition of these partial products using full adders. Okay. So, in order to generate these partial products, how many AND gates are required? In each partial product we require 8 AND gates, and total 8 partial products. So, total 8 into 8 64 AND gates. So, this is 1, 2, 3, 4, 5, 6, 7, 8. So, like that total 64 AND gates are required. Okay. So, we can write directly AND the keyword primitive and we can obtain this, and all the outputs of these AND gates we will assign some wires, okay, because the outputs of these AND gates we have to use to generate the final product terms. Okay. And then in the second row, to get P1, what you have to do? A1 B0 A0 B1 you have to add. Of course, this you can perform with half adder also, but to have the uniformity I will make the third bit as 0 and I will use full adder to perform this. Then to perform this, so these 3 bits are directly there, but here you may get one carry from here also. So, total 4 bits we have to add. So, we require one full adder, one half adder, but to have the uniformity again I will use all full adders only. If it requires only 2 bits, third bit I will make as 0. Okay. So, this table is shown in the next slide. We can see that A0 B0, I am not showing the AND gate here. So, total I am using 64 AND gates to generate all the product terms. So, this is generated through AND gate with A0 B0 as the inputs, output is A0 B0. So, this itself is your P0. Okay. Then P1 is, as I have told, A1 B0 plus A0 B1, the third input here I have not shown, this is 0. Okay. For all this is 0, this is 0. In fact, for this half adders are enough, but to have the uniformity, because we can instantiate Fourier adders. So, I am implementing the entire algorithm using only full adders. Okay. So, that is why the third bit I make as zeros. So, we can see here this A1 B0 plus A0 B1, A1 B0 plus A1 A0 B1. So, and 0 full adder, the sum bit is this. Along with this carry bit we have to perform addition of 3 more bits. So, this A3 B0 A1 B1 A0 B2 along with this carry. So, that will be performed by using this. So, you are adding 2 bits along with the carry, then you will get sum and carry, this sum and the third bit, then other bit will make as 0. So, that you will get P2. So, like that we can easily verify. So, this table can be mapped onto this architecture. There is a one-to-one mapping is there. Now, we will first write the Verilog code for the Braun multiplier, and then we will just repeat the codes of ripple carry adder which we have discussed in the earlier lectures, and then D flip flop. Then finally, we will instantiate all these 3 blocks to implement the final 3-tap FIR filter. Okay. So, this is the basic module for the Braun multiplier. So, this is 8 bit input, 8 bit output, okay, and product output is 16 bit P0 to P15. Then we require the buffers, as I have told, at the output of each AND gate we need a buffer, because that output of the AND gate we have to give as input for the full adders. Okay. So, we require total of 63 buffers, and similarly, so carry buffers we require 55, okay, sum buffers 41. So, the first product 0 is simply A0 B0, because we do not need any full adders. Here we do not need any full adder to generate P0. Okay. For P1 we are using A1 B0 and then using AND gate. So, we have to generate all the product terms, that is why these many AND gates are 64 AND gates total. This is one AND gate, remaining all are 64 AND gates. Okay. This is straightforward, this one. After the AND gates, for the next one is full adder. Okay. So, we have to generate this full adder code, this we have already discussed in the earlier lectures. So, we can easily go through this one. So, using this full adder we will instantiate these full adders in the Braun multiplier. So, how many such full adders are required? 8 into 7, 56 such full adders are required. So, you can see here full adder 1 to full adder 56. So, total 56 full adders are required, and based on these values we have to assign the inputs and outputs of the full adder module, that is the end module. That is. So, this Braun multiplier will give all the product terms from P0 to P15. Okay, now we have the multiplication Verilog code, the full adder, okay, and then using full adder we can construct the ripple carry adder, and then for D flip flop we have some code. Finally, we will implement the FIR filter. So, this is D flip flop. So, in the 3 tap FIR filter we have delays, that delays can be implemented by using the D flip flop. So, this code also we have already explained in the earlier lectures. Then ripple carry adder is basically full adders. Okay. So, this 16-bit ripple carry adder will be having 16 full adders. Okay. We have discussed this ripple carry adder also in the earlier lectures. Okay. So, using these blocks now, ripple carry adder, D flip flop and Braun multiplier, we finally implement the 3 tap FIR filter. This is the Verilog code for 3 tap FIR filter. So, we know that in 3 tap FIR filter we require 3 multiplications, 2 adders, and then this was the diagram that we have discussed earlier. So, these 2 D flip flops, we are using 2 D flip flops for this and this. This is input x of n, and there are 3 multipliers. These are 3 multipliers which multiplies with A, B, C. So, these 3 multipliers will be represented by Braun multiplier M1, M2, M3. So, we are calling this as, instead of A we are calling as H0. This is up to you. Here I have used H0. This is H0, H1, H2, and then 2 adders, ripple carry adders. Because this ripple carry adder size should be 16-bit, because we are multiplying 2 numbers here. So, one is H0 or A. So, this we have taken as 8-bit, x of n we have taken as 8-bit. So, this 8-bit by 8-bit multiplication we have implemented using the Braun multiplier. So, the output of this one will be 16-bit. This is also 16-bit. So, we need a 16-bit adder. Similarly, the output of this 16-bit adder will be, again you will get 17-bit also. So, the carry bit if you neglect, again 16-bit only. This is also 16-bit RCA. Here yn also will get 17-bit, but we are considering the 16-bit by truncating 1 bit. Okay. If you want, you can store here 17 bits also. Second RCA we can implement a 17-bit RCA, so that we can increase the accuracy. Okay. So, this is the Verilog code for 3 tap FIR filter by instantiating 3 multipliers, 2 ripple carry adders, 2 D flip flops, and then always at positive edge we will assign final output, that is the output of this second adder, output of the second adder as the final output. This is final output, this is output of the second adder. Then the corresponding test bench for this one is, this is test bench. So, we have defined all the inputs as the registers, output as a wire, this is module declaration. Okay. Then we have instantiate DUT, I have used the same names for input of the test bench as well as DUT, and here I am going to complement the clock for every 5 nanoseconds. So, initially I have given this is 2 digit decimal 10, this is H0 is 10, H1 is 20, these are decimal values, H2 is 30. Initially I have given the input as 0, okay. After 40 nanoseconds I will make input as 3, after another 10 nanoseconds 1, then 1, these are the values of the x of n, and then finally we have ended the module. So, this is basically the RTL schematic of Braun multiplier. Okay. We can easily see the structure, how this multiplication the products, partial products will be generated. Then we have finally 3-tap FIR filter. So, this is an Braun multiplier, which is the previous one, this is another multiplier, this is another multiplier, this is D flip flop, D flip flop, this is RCA, RCA, and final output block. Okay. This is the total 3-tap FIR filter top module. Then coming for the simulation results of this one. So, initially we have taken this x as 0, if you take 0, whatever this H0, H1, H2, H0 we have taken as 10, H1 we have taken as 20, H2 we have taken as 30. Initially x is equal to x of n is equal to 0. If I assume that the signal is causal, x of n minus 1 will be 0, x of n minus 2 is 0, because the first sample itself is this, previous samples I will assume that 0. Then what is y of n? This into this, S0 into x of 0, 0 plus 0 plus 0, output 0. So, after some time 10 nanoseconds, it seems 40 nanoseconds. So, after 40 nanoseconds, so what you have given is x of n is you have given as 3, this we have given as 3. So, this value becomes this value becomes this. So, previous values becomes 0, 0. So, what is the output? So, these two are zeros. So, H1 multiplication factor is 0, H2 is also 0, but H0 is 10. So, 3 into 10 you will get 30 value. So, you can see here 30 value. So, after some time we have given x of n as 1, x of n as 1. So, the previous value 3 becomes x of n minus 1, okay. X of n minus 1 means you have to multiply with 20. So, 1 into H0 is 10 plus the previous value is 3 into 20, which is equal to 70, you can see here. So, after another 40 nanoseconds, x of n we have given as, x of n you have given as 2. So, this is 3, this is 1, this is 2. 2. So, this 2 will be now with H0. So, 2 into 10, the previous value is 1, 1 with H1 plus 1 into 20 plus, and the previous value is 3, 3 into H2 which is 30. So, this is equal to 20 plus 20 plus 90, 130. You can see here. This is 2 into 10, the latest value is x of n is 2, 2 into 10, 20, 1 into 20, H1, H0, H1, H2 are 10, 20, 30, right? 10, 20, 30. So, this is 1 into 20 and 3 into 30. This you should get 130. So, this is how you can verify the operation of this 3-tap FIR filter. Okay. So, next we will discuss about the IR filter implementation, but this time while implementing the IR filter we will use a signed multiplier. Okay. So, there are different types of signed multipliers. So, first I will discuss about the signed multipliers, and then using signed multipliers I will show the representation of or the implementation of IR filter. Okay. Thank you.